Hi, my name's Chris Collison, and we're continuing our journey in quantum mechanics towards the hydrogen atom. And what we've just been looking at is the rigid rotor. And what we want to now do is take our Hamiltonian operator that we've developed in terms of spherical coordinates. Remember, we described how that was quite a tedious process to go from Cartesian coordinates to spherical coordinates. So we're going to accept the Hamiltonian operator as it is. We're going to plug that into a Schrodinger equation now and recognize that for the rigid rotor, we only care about the theta and phi term. So because r is constant, we're going to be working only with a theta and phi term. So let's go take a look at that Schrodinger equation. So let's very simply, of course, we can write h hat y, and I'm going to use a wave function now y that's a function of theta and phi, and that's going to be equal to our eigenvalues e, which we've kind of already seen what those eigenvalues are. And I'm just going to clarify that the orientation, so the orientation of the rigid rotor depends on theta and phi. So let's actually now write down what that Schrodinger equation looks like. Now, working from the Hamiltonian operator that we developed in lecture 17. So this comes out to be minus h bar squared over 2i. That's our partial derivative. So this first term involves theta. Second term seems to involve theta and phi, but that's our Hamiltonian operator, and that's equal to E again times y theta phi. Okay, so what are we going to do now? We're going to do a couple of simplifications. So the first thing we're going to do is we're going to multiply by sine squared theta across the board. And so what would we end up with? It's kind of quite easy to do on the left hand side. I'm actually going to give myself some space on the right hand side in here, and then I'm going to multiply across the board by sine squared theta on both sides of the equation. Let's do that in green. So let's plug in here a sine squared theta. We're going to plug in here a sine squared theta, and we're going to plug in here a sine squared theta. And of course, what you're going to notice is that we can cancel these terms. So we'll, in this particular case, we'll cancel the denominator and the square term. So next, what we're going to do is we're going to bring this function over to the left hand side, and we're also going to divide throughout by the value e. So what we end up getting there is minus h bar squared over 2ei, and then I'm going to show in here that we end up with the sine theta term on top, d by d theta, sine theta di by di theta. We've cancelled our sine squared thetas, so we now have plus di squared by di phi squared, and then we have our y, and now we're going to have minus sine squared theta y theta comma phi, and that's equal to 0. So we've brought the right hand side over to the left hand side. And the second thing that we're going to do now is we're going to now multiply by another factor, and that factor is going to be called, we're going to multiply by minus beta, and minus beta well, beta basically is going to be equal to h bar squared over 2ie. So this ends up being, we're going to multiply by minus 2ie over h bar squared. And what you're going to obviously recognize is that when we do this, what we're going to end up doing, by the way, when we multiply by minus 2ie over h bar squared, this term is going to disappear when we do that. And again, because we're going to simplify things, we're going to end up with a beta in here. So let's rewrite that expression. This finally comes out to be sine theta di by di theta, sine theta di y by di theta. So we're going to now bring that y inside our bracket here, plus d squared y by, or di squared y by di phi squared. Okay, and now this will end up being plus beta sine squared theta times y, which is again a function of theta and phi, and that is equal to 0. So let's just clarify this a little bit. So we've got a final expression here, a sort of simplified version of the Schrodinger equation, if you will. And again, what have we done? We've replaced that. Let's remember that beta is equal to 2ie over h bar squared. So, okay, now what? What are we going to do with this? Well, you'll be happy to know that we're going to go back to some work that we found from chapter 2. We're going to use our separation of variables approach. So let's take this to the next slide and see what we can do with that. So when we remember our separation of variables approach, okay, what we want to do is, well, we're going to try to separate this into two terms. One term is going to be a theta term, and one term is going to be a phi term. So it makes sense to say, well, let's have y, which we remember as a function of theta and phi. Let's have that be equal to a theta function. So this is my capital theta. So it's a theta function multiplied by a phi function. This is my phi function. And what I'm now going to do is plug that in to my equation in here. And so what else do we do in this particular case? We substitute. So we're going to first substitute for y, and then second we're going to divide by y, so that we can end up separating our terms. So let's do it one at a time. Okay, so what we end up with is, first of all, the sine theta term, and then we're going to take our phi function and we're going to bring that outside of the derivative. So now we end up with, then we end up with plus so we've now substituted the two terms for y. So we've been able to bring out these functions outside of the derivative. So we've separated those variables. Next, of course, we're going to divide by y. So what do we end up getting? So we end up now getting sine theta, divide by y. So when we divide by y, we're effectively dividing by this portion. So the phi term cancels, and we're left with the theta function on the bottom. So d by d theta, sine theta d theta by d theta, plus, so this term will cancel, so we get 1 over, and there's our capital phi term in here, d squared, and in this case this term just ends up disappearing, right? So we end up with beta sine squared theta equals 0. And so the next thing we're going to do finally is we're going to say, okay, we've got a theta term in here, we got a term in here that only depends on theta, and we got a term in here that only depends on phi. So let's collect those terms together. And so we end up with sine theta over theta d by d theta sine theta plus 1 over. So we now have what we're going to recognize here as our phi function, and then over here we got our theta function. And it turns out that with the separation of variables, what we're going to claim is, again changing back colors in here a second, we're going to set this to be, remember we can independently vary theta, we can independently vary phi. So we're going to make this first term, we're going to say that that's equal to some constant m squared, and we're also going to say this second term in here we're going to be equal to some constant minus m squared. So m is going to be a constant. We can vary these terms independently so that we can end up with whatever value we want because of those independently changing variables. Why do we use an m squared? So the m squared is used in anticipation of using a square of a separation constant later. In other words, by using m squared here and here, we're going to find that something's going to get a little bit simpler as we go forward, right? So we'll come to that. So what I'm finally going to do in this particular section is just write down again our two functions, and the idea will be now is to solve each of these. So let me write that down in the next slide. So we've got our d squared phi by d phi squared term is going to be equal to minus m squared phi of phi. And so that's the first thing we're going to solve. That's the phi function. And the next thing, of course, we're going to solve beyond that will be the theta function. So that will be sine theta over capital theta of theta d by d theta sine theta. Okay, so I know which one I'd want to start with first. We're going to find that the second of these two equations is a little bit more complicated, but we're going to find this first equation in here is fairly straightforward. So we're going to work on solving that differential equation first and see what function fits, see if you can figure it out before we get to the next lecture. So thanks for listening.